Alright, silly people, let's get back to work, shall we? We're going to be, first of all, verifying that this here matrix is Hermitian. So we're going to be checking if the transpose of this guy and then the complex conjugate of said transpose is equal to itself. So what I'm going to do is I'm going to take the transpose of it first of all, but write all of the elements that have complex values on it as complex conjugates of said values, and then actually apply those complex conjugates. This is going to be 1 plus I down here, 1 minus I down here, and 0. Hey, look, it's the exact same as the matrix that we were given. So, is Hermitian? We can keep going. Next bit is to find the eigenvalues, and note that they are in fact real. The process for finding eigenvalues will start by taking the determinant of T minus lambda times the identity matrix I. That's the 2D identity matrix here, and setting the determinant equal to 0. So we're going to be finding the determinant of 1 minus lambda, 1 plus lambda, 1 minus I minus lambda, and setting that equal to 0. And of course that determinant is just going to be minus lambda times 1 minus lambda plus, or actually, minus 1 plus I times 1 minus I. This thing is going to be our best friend in this problem. It's going to pop up a lot. So let's make sure to note the result very clearly whenever we finish this calculation here. Expanding the lambda term, though, we have minus lambda plus lambda squared. We got minus 1 times 1, so 1, plus I minus I minus I squared. And so 1, well, the i's cancel out first of all, and then minus I squared is also 1, so we have 1 plus 1 inside the brackets. So the solution to that ended up being 2. So we have minus 2 equals 0, right? And then we can just factor that out. We can have lambda plus 1, lambda minus 2 equals 0. That's an equivalent statement. And we'll see that the solutions are minus 1. That's what I'm going to call lambda 1. And then lambda 2 is at positive 2. Those are the eigenvalues, right? And then we're going to find the eigenvectors. The eigenvectors will follow from these equations. T times v1 equals lambda 1 v1, and t v2 equals lambda 2 v2. Right? So just multiplying t by a vector that we don't really know yet, so it's going to be 1, 1 plus I, 1 minus I, 0 times alpha, beta, just calling the components alpha and beta right now, equals, and I'm going to use lambda 1 on the right hand side, so it's going to be minus 1 times alpha beta. Carrying out the matrix multiplication on the left hand side, we have alpha plus beta times 1 minus I, and then alpha times 1 plus I equals minus alpha minus beta. But we really only need the first element of those to solve for this. So we have alpha plus beta times 1 minus I equals minus alpha. Adding up the alphas on either side, we'll have 2 alpha equals minus beta times 1 minus I. And that's it, actually. And then if you plug this solution into the other element here, that gives you a different equation. You're just going to find that one of the variables is free. That is the case for pretty much every eigenvector problem. That's why I'm going to solve this for beta and have it be 2 alpha divided by I minus 1 here, and then just define alpha to be I minus 1, so that beta will be, of course, just 2. So that means that v1 is I minus 1, 2, the vector, but times some normalization constant, which we now have to find. So that will be found by taking the norm of the vector and setting it equal to 1. So we've got, or I guess the inner product of the vector with itself and set it equal to 1. That will give you c squared minus I minus 1, 2 times I minus 1, 2 equals 1. So c squared times minus 1 plus I, 1 minus I, and I guess to get it to be 1 minus I over there, I'm going to distribute the minus sign like this, so it's 1 minus I. And I did that because, look, it's this guy again, this thing that showed up before, which we know results in 2 now. So this is going to be 2 plus 2 squared, actually. And so we've got c squared plus, or c squared times 2 plus 4 makes 6, so we've got c equals 1 over root 6, and we will take that to the bank. v1 is going to be 1 over root 6 I minus 1, 2. Okay. And we can move on to the next bit of the problem, which is v2. Same sort of deal. We're going to be solving the equation for by 1, 1 plus I, 1 minus I, 0 times a, b. Don't know what a and b are yet, but it's going to be equal to the second eigenvalue, which happened to be 2, times the same vector. So we've got the same sort of equation going on this side. We've got 1a, so we'll just write it as a plus b times 1 minus I, and then 1 plus I times a on the other element is equal to 2a, 2b. So just taking the first two elements of those and setting them equal to each other, we got a plus b times 1 minus I equal to 2a, and then the a's on either side will cancel out. We'll get b times 1 minus I equals a, and so b equals a over 1 minus I. So at this point we can set a to 1 minus I, and so it will follow from that equation that b is equal to 1. So we'll find that v2 is actually just some normalization constant c times 1 minus I, 1. And we do have to go about finding that normalization factor. Same method as before. We take the inner product of v2 with itself and set it equal to 1. So we've got c squared 1 plus I, and then the other element of that was 1 times the column vector 1 minus I, 1. So we've got c squared, open bracket, 1 plus I, 1 minus I plus 1. This guy again. So it's c squared times 2 plus 1. So it's 3c squared. That we set equal to 1, so we see that c is equal to 1 over root 3. So pretty nicely, we got v2 is equal to 1 over root 3 times 1 minus I, 1. And that'll do for the eigenvectors. The next bit is to construct the matrix which diagonalizes T from the eigenvectors and prove that it does actually diagonalize it explicitly. So the way to do that is you create the inverse S And then the columns of this guy are going to just end up being the columns of the eigenvectors. So column 1 is going to be the first eigenvector, so 1 over root 6 times I minus 1, 2. So I'll write it like this, I minus 1 over root 6, and then 2 over root 6, right? Yeah. Okay. Just making sure, because this can be finicky. And then the other column here is going to be eigenvector 2, so it's going to be 1 minus I over root 3 down here. And then it's going to be 1 over root 3 for this last element. We can simplify that by factoring out overall 1 over root 3, which is going to give us I minus 1 over root 2, and then 2 over root 2, but 2 over root 2 is just root 2, so I'll write it like that. 1 minus I here, and then just 1 here. Fantastic. That's going to be the matrix which diagonalizes T, right? To get the non-inverse form of that, we'll take the complex conjugate of the inverse, since it is unitary, or the Hermitian adjoint of the inverse. For you freaks out there, it's a Hermitian adjoint, not a complex conjugate, but it is just going to be 1 over root 3 times minus I minus 1 over root 2, 1 plus I root 2, 1. Cool. So now we can set up that T will be equal to S, T, S inverse, or actually the diagonal version of T. So I won't even write anything on the left-hand side. ST, S inverse should give the matrix minus 2, or minus 1, 0, 0, 2, the way that we've set it up. Okay, but we actually have to prove that. So we've got minus 1 minus I over root 2, 1 plus I root 2, 1. It's all going to be multiplied by a factor of 1 over 3. And then we've got the matrix that is T, so it's just 1, 1 plus I, 1 minus I, 0. And then times the S inverse matrix, which was 1, or actually I minus 1 over root 2, 1 minus I, root 2, 1. Okay, and now we just do a little bit of multiplication on these here matrices. So I'm going to multiply actually the last two matrices together, first of all. So we've got 1 times I minus 1 over root 2. That just makes I minus 1 over root 2. Plus, it's going to be 1 minus I times root 2. So root 2, 1 minus I. Cool. And then we've got here 1 minus I times 1. So just 1 minus I. And then also 1 minus I times 1, so plus 1 minus I. And then we've got 1 plus I times a minus sign times 1 minus I. Just flipping the signs there for fun. Over root 2. What's that term? And then down here we also have 1 plus I with a minus sign on it times 1. Alright, well, actually, we don't even need the minus sign. Let's not throw that in. It's just 1 plus I times 1 minus I. Okay. Beautiful. I'm going to simplify the matrix on the right before we move on into multiplying the other matrix through, because it is looking right complicated right now. But it looks like, since we know that root 2 is equal to 2 over root 2, we can actually put this term in the same fraction as this guy. So we've got I minus 1 plus, and then I'm going to have it be multiplied by 2, I guess. I minus 1 over root 2. So what we'll do up there. Down here, we know that this term, this very cool term that we've done several times already, just results in 2. This is going to be 2 times 1 minus I, and we'll leave it like that. This is going to give you 2 as well. And then we get, simplifying even further, minus I minus 1 over root 2, 1 plus I root 2, 1. I'm getting pretty sloppy on that one. That's too many lines. This is I minus 1 plus 2 minus 2I. This is minus root 2. This is all over root 2 up here. This is still 2 times 1 minus I, and this is still 2. And then the final line of simplification on that matrix will be here. 1 plus I root 2, 1. Just simplifying it one more time, looks like we've got I minus 2I, so minus I, and then minus 1 plus 2, so plus 1. So it is actually just 1 minus I up here, divided by root 2. And then this element is minus root 2. And this is 2 times 1 minus I, and this is 2. Glorious. Now we can do the rest of the multiplication. So we got 1/3 of, and then I'm going to use big matrix here. Looks like we've got minus sign times 1 plus I times 1 minus I over 2 plus, and then it's going to be 2 root 2 minus root 2, so minus 2 here. Sure. And then this guy is going to be minus, oh my god, this is already getting very heady, but it is just minus sign 1 plus I, 1 minus I, 2 all over root 2 plus 2 root 2. And now we got, in this element down here, just 1 plus I, 1 minus I, all over root 2, minus root 2. And finally, it's 2 times 1 plus I, 1 minus I, plus 2. Cool. Okay. All of these multiplications we've seen before, so we can simplify this greatly already. Because that's going to be minus 2 over 2 minus 2. That's going to be 2 over root 2 minus root 2. That is going to be minus 4 over root 2 plus 2 over, or just 2 root 2. And this guy down here is going to be 4 plus 2. Right. So we've got 1/3 of minus 1 minus 2 makes minus 3. 2 over root 2 is the same as root 2, so these terms actually cancel. 2 root 2 turns out is the same as 4 over root 2. Yeah, so these terms cancel as well. So we got 0, 0, 6. and then applying the 1/3 factor through the matrix, we get minus 1, 0, 0, 2. Hey, we got it. So that is actually exactly what we were looking for. That's even what I said it would look like, all the way back up here. So that is looking pretty solid. Yeah. So then the last part of the problem is to check that the determinant of t and the trace of t are the same for t as they are for the diagonalized forms. So that is just saying that the determinant formed by 1, 1 plus I, 1 minus I, 0 is the same as the determinant formed by minus 1, 0, 0, 2. The determinant on the left-hand side is just actually minus times 1 plus I times 1 minus I. And on the right-hand side, it's actually minus 2. So we've got minus 2 equals minus 2. We are good there. And then also the trace of the matrix itself, T, 1 plus I, 1 minus I is 0, should be equal to the trace of minus 1, 0, 0, 2. If you don't remember, their trace is whenever you just add together all of the diagonal elements, right? So the trace of this guy is just 1 plus 0, so 1. On the right-hand side, it's minus 1 plus 2, so minus 1 plus 2. Does 1 equal 1? I think it does. So everything is verified, and that is how to do Hermitian matrices.